So thank you for inviting me, and this is a very enjoyable symposium. I am not able to attend all of it because of the time difference, and I wish I could be there in person, but I do appreciate the effort that the organizers have made to have the online participation possible, and also for it, inviting my students to attend there and present posters. Um, so today I'm going to talk a little bit about some ideas that have been developing, mostly in the context of the Earth Life Science Institute, where I work at the Tokyo Institute of Technology. And it's this idea that I've been calling planetary hysteresis, um, which in hysteresis is basically memory effects, how past influences the future, and hopefully I'll make this much more clear in the talk that's coming. Um, about the Earth Life Science Institute, it's was established in December 2012 at the Tokyo Institute of Technology as a world premier international research center. And the idea of the Earth Life Science Institute is that the Earth and life are intimately coupled and inseparable from one another. Um, they're basically the same system that are intertwined, and we cannot understand one without the other. And we seek to, as our most ambitious goal, to understand the origin of Earth and life as a system, and of course their coevolution through time. And our strategy is through an open system exchange of ideas between different research fields and breaking down boundaries between disciplines. So this is what we're about, and I hope that everyone here can come and visit us sometime. You're welcome to come to ELSI and join in this fun environment that we've created there. So to begin, I'd like to just ask you to think about a key event that happened in your life that changed the course of your entire life. You know, all of us can think of something that happened to us, a person we met, an experience we had, something we saw that really had a big impact on the direction that our life took. Um, and I think this is an important thing to think about more generally. You know, now that you're thinking about that, think about what kind of event can happen to a planet that forever alters the course of its evolution in a similar way. And what I'm thinking about is something that's a singular, very special, very unique event that um, changes how the planet evolves with time, and which shapes it forever. If we think about this kind of planetary history as a kind of decision tree, or going through these key moments in the lifetime of the planet, from its formation through its evolution in time, we could think about this. For example, we start with the nebula on the left, and the nebula is going to condense, and material is going to aggregate into planetesimals, and then those are going to come together to form planets. There are key moments that happen in the progression of the growth and evolution of a planet, and maybe there's a probability that it goes in one direction or another direction at each of these forks in the road that occur, these kind of bifurcations in the planet's history that are going to ultimately determine what kind of planet it becomes. And there's a series of these events that occur. We can imagine laying it out as a binary decision. So let's say that if a planet takes the decision to go up with some probability P0, or down with probability P1, and we follow this all the way through to the tree, we end up with a probability distribution for the outcomes of different kind of planets, depending on the probability of the whole chain of probabilities that connect from the very beginning to the outcome. And ultimately, this is something that we can maybe observe if we look at, for example, exoplanets. we see the distribution of different traits and different aspects of a planet, especially if we can get more detailed information than we can currently get for exoplanets, then perhaps we might be able to understand how these key moments occur and what the evolutionary landscape looks like that brings about the result of the planets that we actually see in the sky. An example of key moments can be, variations in how the nebula condenses, which affect the chemical composition of the planet, whether it has giant impacts or not, like embryo collisions, whether those are early or late in the planet's formation, whether it has a moon or several, and so on. There's a lot of different things that can happen along the path to building a planet, especially in the early stages, which will determine what the planet is like later on and what the planet's capable of producing. We can also think about, key events in human evolution in our relationship with the planet. This is an example that there's this Toba catastrophe theory, which proposes that the eruption of Mount Toba 74,000 years ago created a bottleneck in human evolution. And this is often invoked to explain the low genetic diversity of Homo sapiens relative to other primates. So I'm just putting this out there to show that there are a lot of key events, a lot of chance or stochastic or random things that can happen, which exert a very strong control on the evolution of these complex systems on the planet. So after throwing those questions out there, so what can we do to try and make this more systematic or try to have a better understanding of how this kind of thing works? This is an unsolved problem, and I've just been thinking about this for a while, and I'm trying to systematize it. And so what I'm going to do is take you through a number of thoughts on how we might view planetary hysteresis and basically the path dependence of a planet's evolution. So I'll talk a little bit about states and processes, and I want to talk about memory and how we can have memory in these systems, and as well as both passive and active memory, which I'll explain in a minute, and then process hysteresis. And hopefully we'll start to get towards a more interesting understanding of this. And I won't be able to answer any questions, but I'll be able to ask some good questions. So we can look at things like, habitability, which is a very key topic that very many people are interested in understanding whether other planets outside of the solar system are habitable. And when we're looking at exoplanets, it's one of the first things that people ask is whether the planet resides in a Goldilocks zone, a place where, liquid water can remain stable on the surface, for example. There was this interesting paper that Adrian Lenardic and his student, Johnny Seals, published recently. And they said, well, what if habitability is a process variable rather than a state variable? State variable would be something like whether there's water on the surface of the planet, whereas a process variable has more to do with what the planet's doing, what are the processes that are actually working. And I think that they're definitely thinking about this very similarly to the way I do. So here's a picture of just like the habitable zone, the Goldilocks scenario. If the planet's too close to the host star, it's too hot, too far, it's too cold. And then there's this location where it's just right. And of course, if you have the CHONPS, the CHOMPS chemical components, then you put all this together, then that's the way to make life. But this is a very material-oriented point of view. And what makes a planet habitable, on the other hand, depends a lot more on what the planet does. If you put all these things together on a planet, there's a lot of things that could still go wrong, and you still wouldn't get life, even if you had everything just right. For example, plate tectonics is very nice for life because it refreshes the planetary surface, and that keeps chemical gradients alive things that drive metabolisms for primary producers in the kingdom of life. The only inhabited planet we know is the Earth, which exhibits a very astonishing number of interdependencies that we are only beginning to really understand. So to move towards this idea, so let's look at this word process. You know, when we say, well, maybe habitability is a process variable rather than a state variable, what do we mean by process? Well, I think a simplest definition of process is something that gives rise to a change of state. So it's the arrow that takes it from state A to state B. And of course, in this sense, process simply means change, right? However, we can break down processes in the kinds of change that they produce. And also, we're interested in spontaneous natural processes, which obey certain rules. There's entropy increase, they reduce the free energy, things like that. Examples of very simple processes are such as diffusion, strain, or gravity. So diffusion is, you can imagine, taking a heterogeneous system, let diffusion work, and then it becomes mixed and very uniform and smooth. Strain, where you take an object which has one shape and you deform it into another shape. Or gravity, where something goes from a higher to a lower position. So these are very simple, basic processes. There are very many of these that we could think about. There are also processes that are composites of simpler processes. Rayleigh-Benard thermal convection is one of these, where you have gravity, thermal expansion, viscosity, and thermal diffusion collaborating together, working together to produce this phenomena, which is much more complex and much more rich in character than any of these simpler processes are able to produce on their own. And in this sense, we have emergent phenomena where when you get simpler processes together and you combine them, you get new phenomena that do not exist without their collaboration. You know, we could think of a lot of examples geologically as well, like rock weathering is a collaboration between precipitation, thermal expansion and contraction, wind, freezing, thawing, dissolution, exsolution, plant growth and decay, all these things collaborating to produce the composite phenomena of rock weathering, which is can produce these very beautiful structures, very interesting results. We can also think of biology as process collaboration, like Homo sapiens and other mammals, of course, as being a collaboration between these processes of respiration and digestion and nervous system signaling and muscular contraction and all these other things that are processes that are collaborating to make ourselves as an organism possible. And so we are a composite process of sub-processes. And even these sub-processes are composites of sub-processes. And you can see that this becomes a very rich way of looking at things very, very quickly. So the next question, once we have this idea of process, how does a planet remember key events in the past in a manner that allows it to influence the future evolution? So I asked the question early on, what can you do to a planet that forever changes its evolution and its behavior? And of course, if whatever that thing you do is forgotten or is not remembered by the system, then it cannot have any influence. So there has to be some aspect, some way that the information of past events is passed on to the future. And I call this memory. So basically, memory is when the process and the change from state A to state B imprints some record onto the new state. And this is what makes geology possible, right? If we didn't have this, and we couldn't look at a rock and analyze it to try and figure out how that rock was formed, or what the environment was, or what the scenario was that gave rise to these rocks in the past. So the whole science of geology is really connected to this idea of memory, that the systems that we're analyzing, the outcomes of geology, allow us to figure out what happened in the past. And then there's two kinds of memory. One is a passive memory, which simply records the process. You can look at it, you can analyze it, and it tells you about what happened in the past. That's just a passive memory, if that's the only thing that it does. On the other hand, there's active memory, where there's a feedback between the imprinted information and the processes that are imprinting the information. So if the memory is causing a change in state, which changes the behavior of the system, which causes the changes of the future processes, and you can get these feedbacks, and in fact, the processes can change the rules of the game as they go, and they can rig the game in their favor. And this is very important idea as well, I think. So what is like a mechanism of memory? If you look at rocks have enormous amount of information stored in them. And the entire mantle of the Earth is a rock, and it's a gigantic rock. If you try to calculate the amount of information that can be stored in the mantle, it's vast. And I've been actually trying to do this recently as just a fun exercise, and it's not straightforward to do. But in any case, there's a lot of information. If you look into a rock and dig into it, even a single grain of sand, one of my professors once said you could tell the history of an entire mountain range written in the single grain of sand, which I thought was a very profound idea. But there's a lot of information there, and we could think of types of whether there's geological passive memory or active memory. A passive memory is actually more difficult to come up with examples than active memory, it turns out. Passive memory could be something like compatible trace elements abundances. So things of which there's very small amounts, but which they're happy to be in whatever phase they're present in the geological materials. So they don't really change the properties so much. Stable isotopes are something that are very useful to infer information about past events, although the stable isotope ratio, especially of very trace species, doesn't have any effect on the physical or chemical properties of the system itself, but it provides a record of the past without altering the future behavior of it. Whereas things like major elements, they can have a very large effect on the behavior of the systems. Incompatible trace elements can have large effects on the behavior of systems. Unstable isotopes can have effects such as production of heat, radiogenic heat. Grain size can have an impact, mixed versus unmixed phases, and there's many examples that I could cite. But active memory turns out to be quite ubiquitous in geological context. This is just one example, and it's a very important one. People have been trying to understand what causes plate tectonics to occur on a planet. And if you go to a paleo shear zone where there used to be a plate tectonic boundary, you find detailed changes in the microstructure. You look at the rocks, you make thin sections and you analyze them, and this is what you see. So at the top, away from the shear zone, you have more or less nice looking rock with crystals that are there's some randomness and there's richness in their distribution and shapes, but they're more or less homogeneous in comparison to what you find inside the shear zone, which is very small grains which have been broken down. they've been dramatically altered by the process of deformation that occurred in that shear zone. And one of the basic ideas of what happens is that the changes that happen in the shear zone are imparting an influence on the system that causes the shear zone to remain weak and reinforces itself. And plate tectonics produces this kind of geology. This is the bathymetry and topography around Japan, and these plate boundaries are there because the lithosphere, the mantle lithosphere, remembers what was done to it in the past, and these things have reinforced themselves. I'm not going to get too much into this, but yeah, the mechanism is that shear deformation causes a change in the structure of the crystals in the rock, and in ways that promote the localization of deformation along narrow zones. Memory effects are also in other places. This is a plot of the mixed layer depth in the oceans. So stratification and mixing in systems is also a form of memory. And these also can be active memory. Especially this one is very important for climate considerations, because the mixed layer determines how much heat is exchanged between the shallow ocean and the atmosphere. So now we move to the state of processes. So there's a state that we can think about in terms of specifying a pressure, volume, temperature, composition in basic thermodynamic sense. But what about the state of processes or dynamical states? So now we zoom out and we think of this at a more meta type of level, where dynamic states are characterized by interactions between processes. And there can be equilibriums that occur between processes when the forward and reverse rates that are determined by these processes are in balance, or non-equilibrium when they're not. But underlying this is a general state of thermodynamic disequilibrium. So these are dynamical states that are running on, they're feeding on available free energy, and they're evolving according to slightly different rules, but these are a different kind of state than we usually think of than thermodynamic states. So now if we go to hysteresis, we want to say what kind of dynamical states and interactions produce memory effects that change the way a system works. There's this idea in fluid dynamics, which is called the subcritical dynamical state, which is one that is sustained only because such a state existed previously. So it's really contingent on active memory. It's a state that's in which the memory of the previous state is what catalyzes the continuance of that state in the future. Arguably, this includes plate tectonics. Earth could continue to manifest plate tectonics even if it is no longer capable of starting plate tectonics from scratch. Because plate tectonics has made plate boundaries in weak zones, shear zones in the lithosphere, it's much easier to keep it going than if it had to create those in the absence of such shear zones. Geomagnetism is another one. Earth could sustain dynamo action in the core, even if it's no longer capable of starting a dynamo up from scratch. In life, it's also argued that life is in a state like this, where it maybe would be impossible for the planet Earth to produce life from scratch today, but because life already exists, it has this property of robustness, and it's diversified, and it has these evolutionary capabilities that allow it to keep going. One of the simplest examples I could talk about is friction. Why is a frictional force or the frictional coefficient depend on whether the interface is moving or not? That's very complicated, actually, what's going on here, but it's the simplest example you can think of. If we were to follow what happens when you slide a block or anything on a surface, if you don't have any sliding to begin with, then you have a precritical state where you increase the tangential over normal force, and you have to get to the static coefficient before sliding can start. And once you do, then you get it into a supercritical state where sliding occurs and can go up and down so long as you stay up there. But what happens is that once you're sliding, you can actually reduce the tangential and normal force below the static coefficient, and the sliding continues. So you have this region between the dynamic and static coefficients where you can have two different states. You can have sliding or no sliding, depending on whether sliding is already happening or not. And that's a very interesting condition. And this is a dynamical state. And then, of course, if you were to drop below the dynamic coefficient, then sliding would stop. If you were to take this through time, you'd see something like this. You'd have precritical rising up above the dynamic coefficient. No sliding is occurring. But once you get above the supercritical, you start sliding, and then you lower the tangential to normal force ratio, and it still continues. It's in the subcritical state. So what we can ask, how much of the processes that are acting in nature and how much of the states that the dynamical states we see are in a subcritical like condition, that they wouldn't be going if they weren't already going. And that the only reason that they're going is because they're going. And that's an interesting thought. I could talk about other things, but there's windblown sand is another good example. I already talked about plate tectonics a little bit, but the stress available to break fresh lithosphere takes it to a supercritical state if you reach that. But once you get there, once you have weak zones, and you can continue. And Earth is arguably in maybe a subcritical state with plate tectonics today, although it does form new plate boundaries sometimes. So but whether that would happen without the existence of pre-existing plate boundaries is not really well determined. Dynamos, I mentioned before, you can have a dynamo start up if you reach the critical magnetic Reynolds number from scratch. Then you could do that. But then once you reduce the critical or the magnetic Reynolds number below the critical value, then the dynamo keeps going. You can have a subcritical dynamo. And there's some discussion about whether Earth's geodynamo is actually operating in a subcritical state or not. And of course, habitability. Why not? You can start up life when you have a certain metabolic power supply. And then you just drive it and you get life going. But once it starts, once life organizes itself, it makes its own catalysts, its own enzymes. Then basically you don't need to have that kind of metabolic power supply any longer, and you can run it in a subcritical state for a very long time. So, like a motorcycle doesn't start up and run by itself. You have to kickstart it, right? This is kind of intuitive in a way. But here's the question I want to leave off with, is what if we had the whole planet? It involves a number of systems that are operating, possibly many of them in subcritical states, maybe not all of them. But you can imagine a collectively subcritical set of states, which are autocatalytic in the sense that they are kickstarting one another constantly and keeping one another going. Now, this idea of autocatalysis is very commonly invoked as a characteristic of biology. It happens at the suborganismic level, so the molecular level, as I mentioned, enzymes and proteins and things like this, all the way up to the ecosystem scale, where you have different species interacting in ways that are beneficial to one another. And of course, you can scale that up the entire planet and think about how the metabolism of creatures living in ecosystems across the planet are all connected to the larger supply of nutrients at the planetary scale. So if we think about this, we can ask a question: is Earth a collectively subcritical planet? In the sense that everything depends on everything else to keep itself going. It's a state of kind of dynamical metastability. And if that's true, then we ought to really think about our planet as well as other planets in a different way. And of course, life would be one of the subcritical components in this sort of context. All right, so I'm going to wrap up there. I just wanted to throw these ideas out there and talk about planetary hysteresis, and to get us thinking about, especially more systematically, and coming up with a new language to describe how planets are very complicated systems, complex systems, and which we have to really try to wrap our heads around how they actually work. You know, we get by a lot on idealizations and crude models, but we often run into problems when those break down, and we try to keep those crude models and assumptions going, but eventually we have to tackle this as a science. And so I hope that we can open this discussion from here on. So thank you, everybody. I'll wrap up at that point.